Yes, I should thank the organizers for putting together what looks like a very nice program. And I wasn't expecting quite as many people, so now I'm all nervous. And I'll try not to write below this line, because sitting there I saw that below some point the board becomes unreadable, but I think we should just put the boards up higher. But I'm not sure everyone sees it that way. So I'm going to talk about finite temperature field theory. Okay, and the motivation is that for much of the history, the early history of the universe, it was hot, and it's under reasonable assumptions it was also close enough to equilibrium that finite temperature field theory is an applicable technique to study it. I'm going to assume some field theory background, roughly, I guess I'll assume Peskin and Schrödinger up to chapter 10 or 11. Is that fair? Is that a problem? Nobody wants to admit. Okay. And as usual, what that means is that I assume that you've heard it and sort of mostly understood it. So that if I say, well, this looks like it's going to turn into a path integral, you say, oh yeah, I remember that happens. Okay. And I'm going to split the lectures into 3 parts and then a few ending remarks. The first part, which will be about 2 lectures, will be equilibrium at equal time. Equilibrium, I'm going to argue, is a good approximation for much of the history, the early history of the universe. And there are some other circumstances beyond cosmology where it's also a useful thing to do. And we'll see that it has its limitations, and that there are also systems or regimes where you're locally near equilibrium. And there we can use something called hydrodynamics. Then there's equilibrium, but trying to study unequal time dynamics. And then there's far from not in equilibrium. And this is arranged, roughly speaking, in order of how thoroughly we can solve these problems. See, here we have good analytical and better numerical tools. Here we have good tools which need some input. Here we have a formalism but we encounter a lot of roadblocks. And here desperate times calls for desperate measures, and we'll do what we can. Okay. I think that mostly this will come to a few remarks at the end. Why, in my opinion, this is not, it's not easy to treat systems far from equilibrium. So let's start with the things we can do. Of course, so here I'm narrowing my considerations quite a bit, both by requiring equilibrium and only studying equal time correlations. And you might say you're throwing out all the interesting physics. And that's not true. And I want to start out by arguing that there are interesting things that you can learn here. So why are we doing this? So much of the history most of cosmological history is expected to be very near equilibrium in the standard picture. And essentially that's because, as we saw in the last lecture, we learned something about the time scales. And when you compare the time scales to the microscopic time scales going on, you find that the time scale is of order the inverse of this Hubble. The inverse of this Hubble time scale, and that's of order the Planck scale over the temperature squared. Whereas the microscopic time scale, microphysics happens on a time scale which is of order 1 over the temperature. And then if I take a ratio, H inverse divided by this microscopic time scale, I find m Planck over T. This is 10 to the 19 GeV. Did this happen to you?
I don't remember. I think that one was not as much. Perhaps you have to block it further. Perhaps I didn't block it completely when I turned it. But actually it's oscillating from left to right.
Tomorrow I'll bring my household oil to see whether that does anything. Okay, divided by the temperature. And that means that as soon as you get below something like 10 to the 16 GeV in temperature, you have lots and lots of time for your system to get to equilibrium. Thousands, millions, billions of microphysical time units. And even if it's not very good at getting to equilibrium, it'll find a way. That's not necessarily true of every feature at every epoch. For instance, we know as the temperature gets lower and lower, the microphysical time scale for weak interactions to occur can become very, very long. And so, for instance, below about an MeV, we know that the weak interactions sort of turn off and can be out of equilibrium. So I'm not claiming that this is always perfect, but at least it means that in many scenarios for many epochs of the history of the universe, we're in good shape. If you're not just doing cosmology, but you're also doing astrophysics, then there are large systems like supernovae, neutron star in spiral, where because of the size of the system, the time scales involved are milliseconds, whereas the microscopic time scales are yoctoseconds, which are again many orders of magnitude apart, and your system will be locally very close to even beta equilibrium. And then there's not quite so large systems. as in heavy ion collisions, where the time scales are several femtometers, and the microscopic scales are 1 femtometer, and there might be a factor of 4 here that it has enough time to equilibrate. So you could hope in these systems that you can learn something as well. But it's less solidly in the regime where you know everything is under control. Okay. So this is the question, is this applicable? I shouldn't have written useful, I should have written applicable. Useful is a separate question. I claim that knowing things about equal time in equilibrium is also useful. For instance, if I want to know a 1-point function, like the expectation value for T00, which is the energy density. This is at 1 point, x and t. And so if I know how to calculate equal time correlation functions, then I can calculate that. I can learn more than that. I can learn about all kinds of fluctuations in my system. So from here, from the energy density, I can learn all my thermodynamics. Well, in a system which has conserved charges, I have to know a little bit more. I have to know the expectation values of those conserved charges. And here, I should clarify that I'm asking this at a specific temperature, and here at a specific temperature and a specific chemical potential. So being able to turn temperatures and chemical potentials into charge densities and energy densities is the same as knowing everything about your thermodynamics. Okay, so if I can determine these 1-point functions, then I know the thermodynamics of my system. What about multi-point functions? In vacuum, if I have an operator phi, then the unequal space correlation function of that operator tells me about the mass of the lightest particle which that operator would create. And here I have vacuum in and out states there. Actually, they're not even in and out states. It's just at one time I'm evaluating a 2-point function in the vacuum. And I claim, and we'll see this a little bit during the lectures, that this behaves at large distances as an exponential whose exponent is controlled by the lightest mass of a particle interpolated by phi. That is, if I act phi on the vacuum, then I get some sum of single and multi-particle states. Pick the one which has the smallest mass, and that's the one that controls this correlation function. And so equal time, unequal space correlation functions have all the information about the spectrum of your theory. What are the particles? What are their masses? It's all in there. Now, does that exactly make sense at finite temperature? Well, that's one of the things we're going to have to find out. What we'll see is that such correlation functions also behave exponentially at finite temperature, but their behavior is modified. And that will teach us something about what's going on in a thermal system. Okay. So that's where we're going. Now we have to get there. And to get there at finite temperature, the tool of preference is the von Neumann representation, where you do everything in terms of density matrices. Finite temperature means that I'm not in a specific state. I'm interested in an ensemble of states. And if that's what you're doing, you can't do it with the standard in-out formalism of quantum field theory. You have to do it using density matrices. So let me remind you very briefly about that. So if you were in vacuum, which I'll go back many times to vacuum because it's the thing most familiar to you probably. And I'm asking one of these correlation functions for instance, between two operators O1 and O2, two different spatial coordinates. And I'm asking about the vacuum to vacuum value. This is sort of a normal thing you would ask in vacuum field theory. In vacuum field theory, you usually want different space-time points. But if you have different space points, then you can use the Lorentz invariance to turn that into anything you want. So this would be enough to know in vacuum field theory. I can rewrite this as trace vacuum, vacuum, operator 1, operator 2. And what does this trace mean? It means that I put a sum over an infinite set of, or a complete set of states with an n here and an n there. Why is that the same thing? Because this n hits this vacuum and requires that n be the vacuum state. At which point I have vacuum, vacuum, and it's the same thing I started with. So that's just a rewriting of the original thing, except now that I can interpret this object as my density matrix and say that I'm taking a trace, this object as my density matrix, and say that I'm taking a trace of my vacuum density matrix times my two operators. That's a good place to start, because I know that the right thing to do at finite temperature is, instead of saying I'm in specifically the vacuum, is to say I'm taking an average over all possible states weighted by their Boltzmann factor. So here I have a sum over every possible state of the expectation value of the thing I want to know in that state, weighted by a Boltzmann factor, with a 1 over z to make sure that my normalization is 1, because z is defined as a sum over all possible states e to the minus beta en. And as usual, beta is 1 over t. And if you believe in Boltzmann's constant, then you would put a Boltzmann's constant here. But the sensible thing is to use temperature units, which are energies, and then Boltzmann constant never has to be written. Can everyone hear me? Am I loud enough? That is such a stupid question. I'm sorry. You have to ask it in a different voice than usual. Am I speaking loudly enough when I'm not yelling like now? Okay. Okay, so here I now note that the sum on n, e to the minus beta en, this en, I could instead, since it's sitting right next to the state n, I could rewrite it as an operator. With my Hamiltonian. I like this because, I mean, this looks like I'm going backwards. Here I have a nice number, and I'm replacing it with an operator. That seems like a bad thing to do. Except this number is different from every n, and this operator is the same for every n. So the n's no longer matter, and they're just part of what we wrote here as the meaning of a trace. And so if I do this, then these n's are now, this is now completely redundant because that's just 1. So I don't have to write it anymore. And so now I can write my expectation value as trace. Here I'll write it for 1 over z trace sum over n e to the minus beta h, operator 1 at x1, operator 2 at x2. Now my point is that this is 1. And so I don't have to write it. So I won't. Okay? So I'm just going to quit writing this. That's actually made my formula simpler. Then the next step is, well, here I have an exponential of an operator. That sounds very nasty. And we all know that the, oh, and sorry, I should have mentioned, you might not be interested in the canonical ensemble. You might be interested in the grand canonical ensemble, in which case you have a mu n there. And I'll call the operator that counts particles n hat. Okay. And so then I would just shift my Hamiltonian by my number, my particle number counting operator, if you want to have chemical potentials. And you can have as many of those as you want. Okay, if you have a system with 5 conserved quantities and you want to have chemical potentials for each of them, then you just need 5 such terms here, and you're now doing the grand canonical ensemble. So there's no problem with that. Okay, but to make the notation simpler, I will not keep writing it, okay, until it becomes necessary at some point in the near future. Okay, so here I have this e to the minus beta h. H is an operator. I'm going to use the, I want to express this in terms of a path integral, because a path integral gives us a technology for doing calculations. And the way you do that is you write e to the minus beta h as a product of a whole bunch of, this isn't really an evolution operator. This is some kind of a statistical operator, but I'm going to write it as a product of a whole bunch of, think of this as an amount of time, and break it up into a whole bunch of very, very short amounts of time. Okay? So I'm going to write it as a product from I goes from 1 to n e to the minus beta h over n, which is e to the minus beta h over n, e to the minus beta h over n many, many times. So lots and lots of factors of e to the minus beta h over n, where there are n copies. And then I'm going to as usual, insert n resolutions of the identity in between here. So n copies of the identity. Each one of these I can write as an integral over what every field could look like at an instant in time. That integral over many, many copies of what every field could look like at every moment of time is in a path integral. And here I'm appealing to your already knowing about path integrals to say that this is going to turn into such a path integral. So here I have an integral d phi, where this means phi is then a function of x, and I'll call it t sub e, where t sub e lies in the interval 0 to beta. And it's just to keep track of where in this series of chopping up of e to the minus beta h am I sitting. The phi at x vector and 0 is the one at the beginning here. This corresponds to n0. Phi at x and beta corresponds to the last of my inserted sets of identities here. And all the ones in between at intermediate values of this parameter, which is not yet really a time, but it's a parameter t, correspond to which of my insertions of identities I have here along the way. Okay, so that's my path integral. It's an integral over n copies of what the field could look like as a classical field, which I distinguish by saying that they have different values of Euclidean time. We'll see in a moment why this is Euclidean time. And when I insert these identities between this exponential, I get, unsurprisingly, something which is essentially measuring the Hamiltonian difference between these two fields. So at this point, I appeal to the fact that you've seen this before, but you've seen it when there's an I in here. Okay, so that all that happens is the thing that you've seen before, wherever there's an I times time, there will now be a minus sign times time. Okay, but otherwise everything will look identical. And so what I have in here is an exponential of minus an integral dt Euclidean d3x of a Lagrangian, but a slightly different Lagrangian. Still my operators. Now, because I've explicitly set a specific set of states, my operators evaluate just to live in that set of states. Okay? And there's one last thing. Because of this trace, at the beginning of this whole sequence, here I have a state n0. Here at the end I have a state nn. This trace connects them. And so phi at x0 equals phi at x beta. The very first at the beginning and the very last at the end fields are identical. Or if you prefer, this path integral is periodic. Okay. I should also remark that at the moment, I'm considering a system with only bosons. I'll have to come back and make a remark what happens if there are fermions. Okay? Where again I'm going to appeal to things that you know about path integrals. Okay? So what is this L Euclidean? Well, it's your normal Lagrangian, but just as I integral dt has turned into minus integral dt Euclidean, that means that t has turned into minus I, no, plus it Euclidean. So too, a time derivative has to turn into a minus I times the time derivative of t Euclidean. That means that if your normal Lagrangian contains minus time derivative of phi squared plus gradient of phi squared, then because you get a minus I for each time derivative, your L Euclidean will be plus time derivative of phi squared plus gradient of a phi squared. So these signs are now the same. That shouldn't surprise you at all, because what I started with here was a Hamiltonian. Hamiltonian has plus time derivative squared plus gradient squared. So all I'm saying is that this thing looks like a Hamiltonian density instead of like a Lagrangian density. Okay? The nice way of saying that is that whereas before we had a metric g mu nu, well, lower mu nu, is minus 1 plus 1 plus 1 plus 1. And I should remark right now, if I'm talking about equilibrium things, I have to make an approximation that I'm not worrying about the expansion of space. The expansion of space automatically means that you're not really exactly in equilibrium. And so, because of the separation of time scales I talked about earlier, if we're thinking about short time scales, then the expansion of space is not a big deal. And I can get away with an approximation that my metric is a constant, in which case I take it to have the flat space unit normalized convention. And I like minus 1 plus 1 plus 1 plus 1. And if you don't, then maybe it's time to change. Okay, you're still young. You still have... The reason this is a good idea is because when I flip the sign of my time component here, I discover that I now have, all that changes is I can write everything in terms of a metric, g mu nu, which is plus 1 plus 1 plus 1 plus 1. The simplest thing it could be. If you use the other metric with a plus minus minus minus, you find yourself with a minus 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 metric, and then you have to go like this and completely change your entire metric convention in the middle of your calculation, which means that every time you go back and forth between doing things this way and trying to do the time domain, you have to rearrange everything, which is an unnecessary complication instead of just sensibly picking this metric. And all that happens is, in these calculations, the funny coordinate time, which you're treating differently than the other ones, changes. And the good old space coordinates, which are just behaving themselves, stay the same. Okay? So that's what's going to happen. Okay. For bosons. So first of all, before we do fermions, which are always slightly more confusing, is this clear so far? Question?
I have got a question. In the third and fourth line under your artificial measure, you wrote something with the psi of x, comma 0 is equal to some projection operator. What is this supposed to be? I don't understand the meaning of it.
Okay, so I insert a complete set of states here.
No, sorry, I don't understand the meaning of this particular equation.
Okay, I should have made a little arrow here. Because I'm not quite saying it's an equality, I'm saying that, yeah, well, actually I am, but okay. So here I have a sum over a complete set of states. The most comfortable way of writing that sum is to write it in the sort of the space representation instead of the momentum space representation. So a complete set of states you can write as an integral over every spatial coordinate space configuration that the fields can take. So a sum over these n's is the same thing as an integral over all values that the field can take. And so the integral over the values the field can take at time 0 is the sum over n0 of that. Sorry, what's really happening is that this is the sum over n0, and this is the sum over nn. That's what's really happening. Each of these integrals corresponds to one of the sums of complete sets of states I inserted here, and the field values themselves correspond to the states that I inserted. Okay, that's what I meant to write. Okay, it's good to ask questions because A, they forced me to clarify things which might not be clear. B, everyone else was wondering the same thing. And C, I don't go as fast when you ask questions. And my average speed is 20% too fast. Okay. Okay, so this is what we do for bosons. It should look familiar, but a little bit different. I have a minus sign here. That's because my time integral, I'm rotating my time to I times the usual time. That's a way of thinking about what's happening. The fact that instead of a minus beta h here, minus I beta h here, I have a minus beta h. It means that I've put an extra factor of I into my times, and that factor shows up then in my time derivatives and flips my Lagrangian to be the Lagrangian as if I had this fully positive or Euclidean metric. And now we have to figure out what happens with the fermions. So two things happen with the fermions. The first is that when I write a Lagrangian for fermions, it's psi bar gamma mu d mu plus m psi. Now some of you are used to seeing an I here. That's because you're used to this metric. You're used to the plus minus minus minus. There would be an I here. In the plus minus 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 metric. Okay. The gamma matrices I want to satisfy a Clifford algebra that the anticommutator is twice g mu nu. Okay. For me, twice g mu nu is minus what it might have been. I don't know who taught your field theory class, but it might be minus what you learned in your field theory class. So if you saw I gamma mu d mu and g mu nu is plus 1, minus 1, minus 1, minus 1, then gamma mu me is I gamma mu u. So I just stick a factor of I onto the gamma matrices that you're used to, and then they satisfy a Clifford algebra for my metric. Now, there are people, I can say this in minds because it's fun, okay? This convention is like Catholicism. Half the world uses it, and they all agree about everything because there's a pope and there's an official set of rules laid down from on high. Yes?
Yes, sir. Well, what do you write?
Is the red a problem?
It's barely readable.
If g mu nu is +1, -1, -1, -1, that's a metric convention which many people use because the Pope uses it. Okay. Then, when I write a gamma matrix, it's I times the gamma matrix you're used to. Okay? So, using this metric convention is like Protestantism. You're starting from the right point of view, and then you fracture in a whole bunch of subgroups who each have their own set of practices which don't agree with each other and make everything confusing. Roughly 40% of the people who use this metric convention put a minus sign in their Clifford algebra so that they can have the same gamma matrices as the Catholics. Think of those as Lutherans. Okay? And then we, Baptists or whatever, use a plus sign here so that the gamma matrices are sensible and Hermitian. Okay? Except in this convention, gamma 0 squared is minus the identity, while gamma 1 squared is plus the identity. So gamma 0 is anti-Hermitian, and the others are all Hermitian. Okay? Pain in the neck. Okay? But we will solve this problem because we now have gamma 0 d0 plus gamma vector d vector, and I want to attach a minus I. So the new thing is I'm sticking a minus I here because that's part of what my time derivative is now in this path integral where I have a minus beta h. Then I need, every time I have a time derivative like here, I need a minus I associated with it. Okay? I'm going to absorb that into what I mean by gamma 0 to something I'll call gamma 0 Euclidean, which has gamma 0 Euclidean squared is plus the identity, which means that I now have a Euclidean set of gamma matrices whose anti-commutator is +2 g mu nu Euclidean, which is +2 times my identity matrix. Okay? So these good gamma matrices satisfy a perfectly sensible, all positive Clifford algebra. Okay? And with that taken care of, now everything looks like you had always lived in Euclidean space from the very beginning of your life. Okay? So the main thing that happens is that I have to put e's on things, say that the Euclidean Lagrangian for fermions is psi bar Euclidean gamma matrices, Euclidean time derivative, or space-time derivatives, plus m. Where Euclidean space-time derivatives means those which use this metric, the all-positive Euclidean metric, and Euclidean gamma matrices means those that satisfy this Clifford algebra, all positive, all Hermitian, all the time. Okay? And there is, of course, one other thing that happens because fermions are a pain in the neck. And that is, oh, where do I have space? I'm going to write this on the top of this one. I could write here and then not everyone will read it. Is that correct? So I write it up here. So I have this series of insertions n1, n1 through nn, nn. And you know, when I do that with fermions, then the sum over the n's is an Grassmann path integral. So it's a d psi 1 bar psi 1 through psi n bar psi n. And then here I have n1, n1, n2, nn minus 1, nn, nn. The periodicity of the trace means that I really want to take this object and move it back to the beginning of this series, so that just as I did here, I can say that the last one and the first one are the same. Okay? But these are Grassmann things. If I want to move this back to here, then I should also move this psi n derivative back to here, so that I'm integrating them in the same or inverted order of how they're appearing in expressions. Oh, but when I do that, this has to move past how many other Grassmann integrations? Well, 2n minus 1, which is, I don't know, some huge number, but it's odd. All that matters is even and odd. Gerade und ungerade. Okay? And this is definitely always an odd number of times. And that means I pick up a minus sign. What minus sign? What does that mean? That means that psi of x0 is minus psi of x beta. So the fermions are anti-periodic, while the bosons are periodic. Okay? So everything looks like the path integral that you've always known, with a few funny little differences. First, everything should be written in terms of the Euclidean metric. So what are the differences? Let's list the differences here. So the first big difference is that usually in a path integral, you have phases. The action is being exponentiated with phases. Now it's being exponentiated with a minus sign. The ultimate root of that minus sign is that we were studying a Boltzmann weighted sum, where higher and higher energy things are less and less likely. And that's why there's a minus sign here. A minus sign is great, because whereas here you have to use this flabby stationary phases, and everything is really divergent unless you put in little I epsilons and stuff, here things are just convergent. Okay? Well, until we integrate over all momenta. But at least, I mean, there aren't masses of phases running around. Things want to converge. Okay, so that actually is a big improvement. The second change is L goes to L Euclidean, which means that G mu nu turns into plus 1 plus 1 plus 1 plus 1. And now time looks almost like space. Almost, but not quite, because the third difference is that instead of integrating from minus infinity to infinity d time, I now integrate from 0 to beta d time. This is a finite range. It's limited by 1 over the temperature. And the fourth difference is, because I now have a finite range, I have to decide what do I do at the ends of that range. What happens at t equals 0 and beta? Are they the same? Are they different? Are they separate? Here, I never really worry about the boundary conditions. Somewhere way off at minus infinity and way off at plus infinity, in the normal thing, I'm supposed to insert the thermal state, whatever that is. And I get away with not caring by giving this very slight I epsilon tilt to my time contour in my integral, which projects to the vacuum on either end. And so I don't really worry about these boundaries. Here I worry about the boundaries, because they're not infinitely far off, they're right there. And the boundaries are that scalar fields are periodic, and spinor fields, let's say bosonic fields are periodic, and fermionic fields are antiperiodic. Now, we're going to do ghosts and stuff like that, because we're going to want to do QCD. That's all the fun stuff, right? Or at least some of us want to do QCD. Some applications of field theory to the early universe, you're mostly interested in scalars and what they're doing, and then you don't need to worry about this. But at some point, you have to worry about ghosts if you're doing non-Beat gauge theory. And the ghosts you think about as being scalar fermionic objects. So are they periodic or antiperiodic? The answer turns out to be, when you go back and you think hard about where they came from, that they are periodic. So it's your spin, not your statistics, that determines this sign. Or if you prefer, the ghosts are there to cancel some fake effects from gauge degrees of freedom. If the gauge degrees of freedom are periodic, you're not going to cancel those effects with something antiperiodic. That's actually the real true reason that they turn out to have a plus. That's the best way of thinking about why they have a plus. Okay? So I didn't derive that, but it's true. Okay, we need to make one other remark here. What happens when I do this path integral and I also have chemical potentials? What happens to this chemical potential times the charge operator? So if I have a bunch of fermions, let's do fermions, because they're the case which is of most interest, for instance, in QCD. So let's just write this for QCD, just for fun. We have S Euclidean means 1 over 4 g squared times a sum on the group index f mu nu a, f mu nu a. And now somebody just told us how important it is to keep track of what's an upper and what's a lower index. Okay, which is true if your metric isn't this. But if your metric is this, who cares? Okay, so I will be cavalier about what's an upper and what's a lower index. Okay? And I can get away with that because my metric is the identity. Okay? So there's the Yang-Mills part. And because of this minus sign, I'm just waiting that the more I'm WEIGHTing, that the more field strength I have, the less likely that configuration is. Okay? And then I have a plus sum over I, where this is my quark type, my flavor, up, down, strange, whatever, strange, psi bar I, gamma mu, d mu. D mu here is del mu minus I a mu a t a minus I a mu electromagnetism qi, where this is the charge of the quark, this is the electromagnetic field, this is the Yang-Mills field, this is my derivative, these are my generators of my representation. And you can think of a chemical potential as being that you're just applying, you're pretending that your charge is like an electrical charge, and you're applying a scalar potential for that electrical charge. Okay? That's the same thing as applying a chemical potential. And so then you would expect to have here, besides this, you would expect to have minus I gamma 0 times mu, where this is the A0 of the fake electrical potential that you're applying, except, wait a minute, an A0 got rotated to an IA0, but this is supposed to be an A0 back in Minkowski space. It shouldn't get rotated. So this I is missing. So when you do the math and you go through the calculation, what really is the charge operator and everything, there isn't an I here. Plus m psi I. Sorry, the chalkboard is 5% too short. So something funny happens here. If you want to apply chemical potentials, you would have thought that there would be an I here, but there isn't. Okay? So it's actually in Euclidean space, it looks different than putting an extra A0 field into here, precisely because since this is a number instead of a real live field that's getting path integraled, it doesn't get rotated by an I. Okay? Also there's a d psi bar psi here. I have to path integral over those guys too. Yes, sorry.
So
question?
writing things in this way, it seems that you are breaking gauge invariance, or not? You're choosing a gauge for A, no? Or not?
Here, I don't have to choose a gauge.
But aren't you specializing A0 to say that it's...
There's no group generator here.
Okay.
So one way of thinking about a chemical potential is that for each flavor of quark, I add an extra gauge field for which only that flavor is charged. Okay? But this gauge field is an external. It's not a physical fluctuating gauge field. It's not here in my path integral. This path integral is over A mu A, the Yang-Mills field. And maybe if I'm allowing my electromagnetic fields to be fluctuating live fields, then they're in there too. But to apply a chemical potential, I add a fake gauge field coupled to each quark flavor, and I just give it a scalar potential value, which is a constant. And that looks exactly the same as applying a chemical potential to the total charge. Okay? Except because that's a constant, it has a finite real value in Minkowski space. When I do this rotation, I should not, since it's a zero component of a field. It acts just like a time or a time derivative and should get a factor of I, but it doesn't because it has a finite real value in Minkowski space. So no I. Is that? So this is gauge invariant and this is gauge invariant under Yang-Mills and electromagnetic gauge rotations because I apply the appropriate rotations to these guys. When I make those gauge transformations, that everything is okay. Okay? And yeah, this is a fake gauge freedom under which I make each flavor have its flavor charge to allow me the handle of attaching a chemical potential. Question?
So that's electromagnetic field there, right?
Yeah, here.
So is it non-dynamical here? I mean, because you don't put the corresponding term in the exercise.
So yeah, if I have it as a live field in my theory, then I also have a 1 over 4 e squared f mu nu em. Yeah, if you want it to be one of the fields that you're really having things happen to, if you want it just as a background that you're trying to study QCD in that, say, in a magnetic field background or something like that, then you would ignore this and you would leave it out of the path integral and put it in as some classical background field. Depends on what you're doing.
Okay, so is it our case? I mean, if we just want to study the...
If you want to study QCD in a magnetic field background, then put this in, leave this out, and don't integrate it.
Okay.
If you want to study the theory of QECD, quest, okay, then path integral it, put it in, put it in. If you want to study QCD and you don't care about electromagnetism, you think that's a tiny correction, I'm going to ignore it, leave it out, leave it out, leave it out. Okay. Question?
So in usual field theory, if I have isolated gamma zero, I would worry about Lorentz invariance.
Yes.
Here,
Okay, so A, you have no Lorentz invariance because your density matrix has a rest frame. B, this only happens if I'm applying a chemical potential, which is another rest frame effect. So that's why I'm not too worried that there's a gamma zero. It is indeed evidence of asking a question which is not Lorentz invariant. But I asked a question that's not Lorentz invariant, so I'm not too surprised. Okay.
Could we promote the whole thing into something which is Lorentz invariant by promoting the chemical potential to like a current, sort of current or something?
The boundaries here are still not Lorentz invariant. You can make it look covariant by making beta a 4 vector. But I'm not convinced that you get much further because you're basically starting with a density matrix which has a rest frame. So there will be some, the microscopics here are, oh, that's an interesting point. This looks like it's just an out and out Lorentz non-invariance. It turns out it isn't. I can perform a field redefinition which absorbs this, makes it completely disappear, except on the t equals 0 or t equals beta surface. And I can have it only live there. Okay? The rest of this thing looks nicely covariant, except these boundaries. That means that microscopically, if I ask about very short distance and time scales, everything looks completely Lorentz invariant. I discover that I'm not Lorentz invariant, that I have a density matrix when I try to travel through space and discover that my time is periodic. So I have Lorentz violation, but it's in some sense very soft because it involves traveling through time and discovering this periodicity. Yes, yes, yes. In fact, secretly, I'm also, at the same time, doing vacuum field theory. Because if I just make beta go to infinity, this integral goes forever. Who cares about boundary conditions that are infinitely far away? then everything is now vacuum field theory, except that I've slightly reduced what I'm allowed to ask. I'm only allowed to ask questions about equal time correlation functions if I want them to correspond to a logical question in my original field theory. I can ask about correlations between things at different TEs, but they, quote, don't mean anything, unquote, in the sense that they don't directly give me a correlation function of my original theory. They may be related by analytical continuation, which we'll talk about in the last lecture, but they don't directly give me such a correlation. Okay. Well, I thought I would no way. Yeah.
Just do a comment. So of course, if you want, for example, conservation of the electromagnetic charge or conservation of the baryon number, the mu I would be related. So you would write one chemical potential for the electromagnetic charge and one chemical potential for the...
Well, I mean, they are conserved. I mean, those things are all conserved in here because of the symmetries of my Lagrangian and path integral. So none of those are a problem.
No, but you are taking as many chemical potential as particles practically.
I'm taking one, I can allow one chemical potential per flavor. And if the weak interactions are not considered, then I can have an up chemical potential, a down chemical potential, a strange chemical potential, etc.
Okay, good.
That's what I'm,
assuming that the electroweak...
yeah, if I turn off the weak interactions, I can do that. If the weak interactions are there, I shouldn't be applying chemical potentials. But in QCD, they may be interesting in many situations. And so I thought I would put them in just for fun. I might, for instance, only put in a mu baryon here or B minus L. Then just put in those. Okay, but I wanted to make one funny point, which is mostly for QCD people, I suppose, and not so much for all cosmology people. This is an integral with a real measure. And it's a positive measure. This thing is a positive quantity. And that means that I can do importance sampling. And that means that instead, what I'm mostly going to talk about next lecture, or hopefully at the end of this one, is a perturbation theory for trying to study this path integral. Okay? That perturbation theory, well, if I'm doing QCD and this coupling gets large, I go to infrared physics, then it's a problem. And it will turn out that I have more infrared problems here than I have in vacuum. So the perturbation theory has its limitations. You could say, screw perturbation theory, just do the path integral, just do it. Okay? Put it on a computer, beat the hell out of it. Okay? That's lattice QCD. We will have lectures about that. It's a useful technique. Lots of people do it. It's a good idea. It has the following limitation. If I have these chemical potentials, then my statement, oh, look, everything here is real and it's positive, is not always true. I can do these bar psi integrals. And what it does is it turns the fermionic part into a determinant. So I get a product over I equals 1 to n flavors, up, down, strange, etc., of determinant of this d slash operator plus m minus mu gamma 0. Okay? And the reason I belabored this point of electromagnetic fields having an I and this mu not having an I is that with the I, it's just like part of this d slash. It obeys this positivity. With this guy here, because there's a matrix here, you should always be nervous about positivity and determinants and things when there's matrices. Okay? It turns out that this thing has phases. It's not always purely real. If I have two fermions with equal m and opposite mu, then I get det d slash plus m minus mu gamma 0 times det d slash plus m plus mu gamma 0. With some work, you can show that this is the star of this. So I can put a minus and a star here. And then I have something that's real and positive. If they have opposite chemical potentials, that means that you can cheerfully study that problem on the lattice. Everything works. People do it. It's fun. But this is a weird case. This is if you have the up and down. Their masses are not very different. We can pretend they're the same. So this isn't a big deal. Baryons, if you want to do physics where you have finite baryon number density, if you want to do neutron stars or heavy ion collisions or things like that, you have a net baryon abundance. That means that usually you have the up quark and the down quark have approximately the same chemical potential. That's the opposite of this case. In that case, the phase in here and the phase in here make each other worse instead of canceling. There used to be an approximation people would make where they said, oh, maybe the phases don't really matter. I'll just throw out the phase and keep the magnitudes of these things. That's the same as replacing a chemical potential for baryons with a chemical potential for pions. And it doesn't work very well. Okay, so that's just a remark. There's a wonderful method where you try to really do this integral. And when you put in chemical potentials, it generically does not work because it encounters phases which ruin the importance sampling. And that's a problem, and the solution to that problem is we don't know. We don't have a solution at this time. Okay? So, I mean, we don't know everything. Not everything works. Okay. I have 15 minutes. So let's erase the boards except, no, we'll erase all the boards. So now we want to look at, so I have this theory, as I said, if the chemical potentials aren't there, I could try to just do this integral by some numerical methods. Now, it's totally not obvious how to do that, so we'll have 4 90-minute lectures about it. And because we have those, I won't talk about it anymore. I'll talk about what do we know analytically, what can we do with, say, perturbation theory. I'll leave that for the moment. So to make the story a little bit more concrete and not too complicated, I'll consider as an example Yukawa theory, where I have a scalar phi and a fermion psi bar and psi. This will be a real scalar just to make life as easy as possible. So that means that my Euclidean Lagrangian is 1/2 del mu phi plus 1/2 m squared phi squared plus lambda over 24 phi to the 4th plus psi bar del slash plus mf psi plus y phi psi bar psi. This is my Yukawa coupling. So the nonlinearities are a Yukawa coupling and a scalar self-coupling. Everything else is quadratic in fields. Okay. My partition function is integral over psi bar psi and phi. The boundary conditions we already talked about. The range of the integrals we already talked about. I then have a exp of minus phi m squared minus box phi over 2 minus psi bar d slash plus mf psi times exp times exp. Here I have oh, sorry, there's an integral here, d4x. Here I also have an integral d4x. Here I have an integral d4x. Here I have minus lambda over 24 phi to the 4th minus y psi bar phi psi. And here, just for fun, because it will be convenient and allow me to calculate correlation functions and do perturbation theory and so on, I'm going to add an external current for my scalar and external fermionic sources for my fermions. Okay, and you should all be familiar with that. When I actually ask about the value of anything real, then I have to set these to 0. But by differentiating with respect to them, that allows me to calculate correlation functions of these fields. And once I put them in there, differentials with respect to these guys give me factors of these things, and in my interaction terms I can replace the fields with differentials with respect to my external currents. So where I have lambda phi to the 4th of y, I can rewrite that as, provided that I stick this exponential in front of the other one. Well, actually, I only have to make sure it's in front of this one. Then lambda phi to the 4th I can write as lambda times minus derivative with respect to j of y to the 4th. And y psi bar phi psi I can write as y times minus j derivative minus eta derivative and plus eta bar derivative. Actually, this is also with a minus because of the ordering thing. I have to put a plus here, don't I? Yeah. And this allows me to develop perturbation theory in the usual fashion. Okay? So I make these substitutions. I pull the interaction part of the, when I do that, then this term no longer has any reference to psi bar psi or phi, and I can pull it out of the path integral. You've all seen this. All that's different is that there's no i's, thank goodness. They're just minus signs. So I can pull it out of the path integral, and then my z of j eta bar is e to the minus integral d4x lambda over 24 minus partial j of y of x to the 4th plus Yukawa partial, which I already wrote here. times an integral which is Gaussian. Where did I want to put a plus? So, yeah. And you all know I can now do this Gaussian integral. And it will give rise to propagators, and this will give rise to interactions. And everything looks exactly like it looked in ordinary quantum field theory, except for the minus signs and something that isn't obvious in this picture but is hidden in this integral, the periodicity and the limited range of my fields. Okay? And what that means is that, first of all, my propagators are 1 over p squared plus m squared for my scalar, and 1 over I p slash plus m for my spinner. You might not be used to this I here. That's because your gamma matrices are I times my gamma matrices. If you're not used to it. If you're used to it, then, you know, good. Careful, p squared here is really p squared. This is p0 squared plus p vector squared. It's positive. And this is a 1. Is this an I or is it a minus I? Am I forgetting an I epsilon? No. This is a 1. These are pluses. No I epsilons. Simple. Okay? This is a 1. No I epsilons. There's just an I here. Because of our choice of gamma matrices, if we picked gamma matrices satisfying a negative Clifford algebra, there would be no I here. But then it would be confusing because p slash would be minus p squared. And I would get mixed up. Okay, so this doesn't look very different. A vertex has the rule minus lambda delta to the 4th of p1 plus p2 plus p3 plus p4. This minus is different. You're used to there being a minus I there. There's a minus I there because you're used to there being I in your action. And now there isn't. There's a minus sign in the action. The minus sign in the Feynman rule here is the minus sign here, which is the overall minus sign in the action. Okay? So this is just a fact that we're in Euclidean space now. Okay? So that's not terribly different. And then I have my Yukawa interaction, and that also has a minus y delta to the 4th of p1 minus p2 plus p3, where here I choose all incoming momenta, and here I choose the outgoing and incoming. So I choose the outcoming fermion to have an outgoing momentum, so I have a minus sign here. So these are normal Feynman rules like you're used to. They're no surprise. Now the surprise. Usually, this propagator, besides this form, this is its, I'm also supposed to put an integral over what this momentum can be. Okay, or if I have a loop, maybe you learned it that you put an integral over the momentum going around the loop. God. And that's where there's a difference. If I have, so let me draw my time direction and the space direction. This is periodic. When I go from here to here, I find myself back where I started. Whereas this is infinite. When you Fourier transform, you know that an infinite x gives you a continuous p, and a finite t gives you a discrete p0. You know that. And so, whereas integrals over momenta in vacuum look like that, now in the thermal setting, there's T times a sum. Times an integral. Why is there a factor of T here? The way to remember why that there's a T here is so the units here and the units here are the same. The reason there's a T here is what happens when you Fourier transform a finite versus an infinite coordinate. Okay? There's a T without a 2 pi. There's a 2 pi spacing here. That's the same as there being a 2 pi downstairs in this integration measure. That keeps all the 2 pi counting the same. Okay? This is rather a big difference, it turns out. And this is often written as sum integral p to make it look tidy. Okay? Whereas this I can write as integral p. This I write as sum integral p. And then you're supposed to know that that means this. And that's true for the bosons. If I have a fermionic loop, then if I have anti-periodicity here, that changes what the available frequencies are. Then I get pi times 2n plus 1 t, and a member of the integers. And it's okay that this doesn't match up with this, because at every vertex I have an even number of these fermionic guys. So the odd half-integer nature follows the fermionic lines. Every fermionic line is always at a p0 value, which is odd half-integer. The bosonic lines are always at an integer. And this I write as sum integral prime. Okay? So if you're used to where you live after you've performed Wick rotation, then these Feynman rules look precisely like the Feynman rules you're used to. Nothing is different, except that integrals are sum integrals. Okay, and that's actually the whole structural difference between temperature and vacuum. I can recover vacuum by just taking T towards 0, in which case the sum, the elements of the sum get closer and closer together and are well approximated by an integral. And then I'm right back in vacuum Euclidean perturbation theory, which is just normal vacuum perturbation theory after you've Wick rotated. Okay, so I think I actually have to stop here, should stop here. It's a good place to stop. Next lecture, we'll talk about what happens to you when you try to study this perturbation theory. But if there are questions, then we can do one or two before we run to lunch. You're all hungry. Question?
Yeah, the correlation functions in Minkowski space-time. is same as the correlation functions in
The equal time correlation functions in Minkowski spacetime are the same as the Euclidean ones. And so as long as you only put all of your operators at one time, everything is fine. If you put them at different times, then the very first step I took doesn't work. And none of this functions. We'll talk about that on Friday. And we'll build the right perturbation theory to handle that, which will unfortunately be a little bit more complicated. Okay.
But there is this axioms, the Osterwalder-Schroeder
Yes.
theorem, which relates certain conditions that we need on the Euclidean field theory to
Right.
satisfy.
Yes.
For that to be equal to.
Right. So the best way of thinking about that is that if you start with a Minkowski thing and you come to this Euclidean thing, it will always satisfy those axioms. If you just write down a Euclidean thing hoping that it corresponds to something sensible in Minkowski space, you need to check those set of conditions. And if it does, everything is good.
Is it proof for QCD? Or because that's what
It's complicated with QCD because of gauge invariance. You have to think carefully about what correlation functions you're willing to ask about. But basically, if you ask about gauge invariant operators, then their correlation functions should obey the Osterwalder-Schroeder. And that's all you should actually ask about. Then their correlation functions should obey the Osterwalder-Schroeder theorems, and everything is fine. If you ask about correlation functions of the field operators gauge fixed, then, well, don't. Yeah.
Let me say a word more on, so I didn't get it why the ghost fields have a plus in the boundary, because I mean, I would say that it only depends on the +1 year nature, because you have to commute.
Okay, so that's not quite true, because the way that I set up this path integral arose from considering psi and psi bar to be things appearing in external states, which got inserted in a complete set of states. The way that I get my ghosts is that I discover that after gauge fixing and doing something and something, I have a determinant. And that determinant has periodic, not antiperiodic boundaries.
Don't appear in the states
right.
So you don't have to commute them through.
Right. So I insert them to describe a determinant which, when you arrive at it, has periodic boundaries. Okay. So I have to put them in with periodic boundaries. Okay. And then if you have additional questions, so feel free to think about questions and spring them on me at the beginning of the next lecture. Okay. But otherwise, maybe we should eat lunch.